On a positive charge, the electric field lines are going outward, and on a negative charge, the electric field lines are terminating at the charge. There's a greater density of electric field lines that represents a stronger electric field. So this one has a stronger electric field than this one. When we have opposite charges, the electric field lines will go for the positive charge and terminate on the electron. When there are like charges, the electric field lines will repel each other. When we're calculating the electric field of continuous distribution, we set up an image like this, and the total electric field at this point is an integral of all the contributions. And we have to figure out the limits of integration, which in this case we start at A and end at A plus L.
So basically, to set up an example problem, we have a point charge with a 10 nanocoulomb charge, and with a distance of 5 centimeters, we want to know the electric field at point P. So we have our equation here for electric field, Ke Q over R squared, and we set it up with Ke, which is of units Newton meters squared over coulomb squared, times 10 nanocoulombs over, we have to change the centimeters into meters before we do the equation, and so we get 0.05 meters squared, which gives us 35,916 newtons per coulomb.
Alright, so electric force is the repulsion and attraction between charged particles. Those charged particles being electrons and protons. Now, as you can see up here, like charges repel, so we have the protons and the electrons repelling each other, but opposite charges attract, causing them to go together. Now, the charge of an electron is 1.602 times 10 to the negative 19. So a positively charged particle will go in the direction with an electric field, while a negative charged particle will go in the direction opposite of the electric field. Now, to find the force of the electric field, we use Coulomb's law, which states Ke times charge 1 times charge 2 all over the radius squared will give us the force. Ke being the constant 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Now, don't forget that this only applies to a point charge and a spherically symmetric object. Now for vector superposition, we're calculating the force on a single charge when multiple charges are present. By adding the sum of each individual charge and using the vector rules, we can find out the total force on it.
Okay, so to set up a problem to find the resultant force on a single charge caused by multiple charges, you have to do superposition, as Jake said. So to set it up, you want to use this equation, the Coulomb's law, and then you take the distance between the charges you're working on, and you find the charges of them, and you plug them in respectively. So the force of particle 1 on particle 3, where we're looking at particle 3, is Ke, the charges, negative 3 microcoulombs, negative 4 microcoulombs, and then the distance is going to be both of these added together because it's that far away, and we end up with 0.431 newtons for a force of the particle 1 on particle 3, and we set it up similarly for the force of particle 2 on particle 3. This is 5 microcoulombs, this is negative 4 microcoulombs. Plug them in. The distance is only 0.2 meters this time, and we find it's negative 4.495 newtons. And then we add them together to find the final force on particle number 3. We get negative 4.064 newtons.
So I'm going to be talking about electric flux, and electric flux is defined as the electric field multiplied by the area of the surface projected in a plane perpendicular to the field. So you take the electric field times the area times cosine theta that the electric field makes with the surface to get the perpendicular component, and that gives you flux. And that's for a straight plane. Now for a curved plane that's not uniform, you would do the area integral, which would just be the area integral of EA cosine theta, once again to get to the perpendicular component. The best analogy that I can think of for flux is air passing through a window. It depends on the strength of the air, or the wind, being the electric field, and the size of the window, being the area. Now, flux is basically how much air passes through this window. Now, the unit for flux is Newton meter squared over Coulomb, and this is derived by taking the electric field, which is Newton coulombs, multiplied by the area, which is meters squared, thus giving you flux equals Newton meter squared over Coulomb. Now, the law that you use in relation to flux is Gauss's law, which is just the charge enclosed over the permittivity. The permittivity being E naught equals 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared, and Gauss's law gives you Q over E naught. Now this form of Gauss's law only works for closed surfaces that the electric field passes through. So those are AKA Gaussian surfaces. To the integral form of Gauss's law, which is just the area integral of E dot dA, which then gives you Q over E naught. Now you use this integral form where the electric field is not constant.
So just a quick example of electric flux. If an electric field is passing through a surface with a width of 2 meters and a height of 2 meters at an angle of 60 degrees to the perpendicular surface, we can just set up EA cosine theta, and the electric field we've given a value of 3,000 newtons per coulomb. So we just plug into our equation, and since it's 2 meters by 2 meters, we just put in 4 meters squared. And cosine of 60, because that's the angle with the surface, we get 6,000 newton meters squared per coulomb.